different forms. They can happen with carbon materials alone in some cases, or carbon materials that are coated with polymers or oxides, and we'll go through some of these things. And you could have both physical charge storage, so that's the double layer effect, and chemical storage in a single entity, or really at a single electrode and active material pair. Okay, so battery electrodes, on the other hand, are completely Faradaic. That means it's all about a charge transfer event, a chemical reaction, in essence. Here's a very general table, a comparison table between batteries and supercapacitors. So a rechargeable battery, it has high energy density and low power density, and a capacitor has those two attributes flipped: low energy, high power. The energy limit for batteries is just the mass of electrodes, just getting enough of your electrode material in there. But the limit for a capacitor is how much surface area you could actually put into the device. That's why having three-dimensional nanostructures is so important for capacitors. The output voltage, as we already mentioned, is relatively stable, whereas it is in discharge for a capacitor, it's always declining aggressively, usually linearly or nearly so, but there are exceptions to that. And then the charge and discharge on batteries is slow. It's fast in capacitors. The other thing about this is, because of the fact that capacitors are using a physical mechanism mainly, they can undergo millions of cycles, whereas typical rechargeable batteries can only reliably do about 1,000 cycles. I mean, here it's listed as, it's low, it's a few hundreds of cycles, and now, maybe you can get to 1,000 cycles or so, but not, I mean, you're talking about losing capacity. If you get a battery that has lost only 20 or 30% of its capacity after 500 cycles, that's a very, very good battery, right? All right, so there are a number of different kinds of supercapacitors. We'll introduce various parts of these as we go, but I wanted you to be able to see this. You have on the left purely double layer capacitors, in which case, again, it's all about getting high surface area. So you use different kinds of carbons, aerogels and activated carbons, and even carbon nano things like nanotubes. That's what drives the effect in double layer capacitors. On the right, you have pseudo capacitors, where you'd put on the surface, in a thin layer, you would put an oxide or a polymer that has a fast surface reaction, a redox reaction. And then there are other forms where you have hybrid capacitors, where you could actually put a battery-like electrode on one side and a capacitor-like electrode on the other side. And if you get your potential matching right with all the reactions that are going on the battery side, you can actually make a device that in part acts like a battery. That means it has maybe a somewhat flatter discharge voltage profile, also has higher energy density, but it would have lower power density, right? So you don't get something for nothing, and it also would be susceptible to that lower cycle life that batteries are. So for supercapacitors, there's a number of electrolytes. I'll talk a little bit more about this in subsequent lectures, as I think Dr. Gupta will as well. So that's part of the materials aspect of supercapacitors. In fact, it may be the most active right now is looking at different electrolytes. So KOH and sulfuric acid are very common aqueous electrolytes. We use them all the time. They're easy to get a hold of. They're not too particularly difficult to handle, although always be safe in the laboratory. Use PPE, use hoods, chemical hoods, and so forth. But they're pretty easy to handle. The second two are organic electrolytes. These are the kinds of things that you'll usually find in commercial supercapacitors. They use organic electrolytes usually. The last category is ionic liquids, which is an area of very, very active research right now. And if you just look at some of the attributes here, what you want to have is, you'd like to have a low density, although the density differences here are not very much, right? You want to have a low resistivity, and there's a huge range of that, right? Aqueous electrolytes are the champions on resistivity, but they suffer on the cell voltage part of this, right? So we also want to have high voltage, because really there's not very many engineered devices that are going to work well with a power storage and power delivery device that's only putting out 1 volt, right? Almost everything that you'd use would be higher voltage. Not quite everything. Some electronics now can work on 1 volt pretty well. But typically, what you want to do is to have voltages that are higher. If you have 2.5 volts, usually that's going to be turned into a 5 volt. You'll just stack those electrodes on each other. You put them in series, and you'll make a higher voltage. Here's what a double-layer capacitor looks like in sort of quasi-artistic form. The way you would form the circuit, you'd have a positive and negative electrode. On the positive electrode, you attract negative ions, electrons, from the electrolyte, and on the negative electrode, you attract positive ions, for example, protons, to it. And what you want to do is you want to have as much surface area as you can on both electrodes, so that you can store the maximum amount of surface charge. There's some significant merits of double-layer capacitors. I think the biggest one is that they're pretty easy to make. You don't have, there's not that much chemistry that goes into them. It's mainly about getting high surface area and getting a reliable electrolyte, and so it's fairly well established. You can do really high power, because this physical charge-discharge process at a surface is extremely reversible, not particularly susceptible to adverse chemical reactions that would happen. And so it's a simple device. The downside is that in order to make these magical ultra-high surface area electrodes, that process can be costly. All right. They also have low energy. So electric double-layer capacitors tend to have really good power characteristics, but very poor energy density characteristics, right? So they're not really contenders to replace batteries. And we'll talk a lot later in this lecture about where they are useful, right? So really, the research directions are listed here. So again, more and better surface area. But then looking at at ionic liquids, because they have that high potential window, that large voltage in a single device that you could use, that's advantageous, instead of stacking these lower voltage 2 electrode pairs on top of each other in order to reach your voltage. So the applications are listed here. Mainly they're in power conditioning and fast charging discharge, energy capturing, burst power a little bit. So they're used, if you have a motor that suddenly is drawing a lot of demand for current, and this can happen, right? I mean, the Tesla all-electric vehicle, it accelerates from 0 to 60 miles an hour in how many seconds? What's that?
2 seconds.
2 seconds. It's crazy. They call that ludicrous mode or something like that. Well, in order to make it do that, it's really not the motor. Getting an electric motor that's powerful enough to do that, it's actually not that hard, because you have a great advantage using electric motors over internal combustion engines, because electric motors have plenty of torque all the time to produce that acceleration, whereas internal combustion engines don't. They don't have good low RPM torque. I'm a mechanical engineer, so I just kind of throwing that in there for those of you who don't know. But the problem is not actually making a motor that could do it. It's getting enough current into that motor so that it can actually go that fast. And Tesla does that in part using supercapacitors, right? It's also good for energy recapture. So regenerative braking in hybrid vehicles is one example, and electric vehicles as well. So pseudo capacitors, I'll call them here, are electric double layer capacitors that are bumped up in performance by adding a surface coating of Faradaic or reactive material that undergoes fast redox reactions. Okay. Usually those are transition metal oxides or conducting polymers, and these reactions happen just within the first nanometer or so of the electrode surface. So that's why it's something that's it's not like a battery, because you're just using a really, really thin layer. And by using a thin layer, it's not as susceptible to this larger scale decrepitation and breakdown. The way a battery usually loses its capacity is that you actually kind of crumble the electrode and it becomes more resistive on the inside, and that leads to more heating, which leads to more side reactions that are irreversible and so forth. But this is all happening in just the surface layer, and so it's much more maintainable. Here are here's a list of pseudocapacitive materials and their relative capacitances. The downside to pseudocapacitive materials is that the best one by far is ruthenium oxide. It's shown here. It has the highest capacitance per unit mass, or specific capacitance, and yet we're still looking for a lot of other things. Why is that? It's because there's not enough ruthenium to make really big versions of this, right? It's too expensive to use ruthenium, okay? And so manganese is a popular, manganese-based, to some extent nickel-based oxides are popular, and they they rival at least some of the ruthenium-based specific capacitances, right? Polymers are lower in specific capacitance than even the manganese oxides, although again competitive. But it's always a trade-off. It could be cost. The polymers, some of these polymers are very simple. Polyaniline is a simple polymer that you can use here. And so this is where you start to engineer a device to say, I want to be able to make something that has a sufficient energy or power density, or is easy or difficult to package. Obviously, you'd want it to be easy for a certain cost. The polymers tend to win on cost. And then on the last case, you have the pseudocapacitance of carbon materials itself, and that's usually coming from surface functionalization of the carbon. The advantages is that you have higher capacity, and in particular energy, right? You have more energy density in these devices, which is the problem with double layer capacitors, is that they're not energy dense enough. They have plenty of power to do almost anything you would want to do, but they're not very energy dense. Pseudocapacitors can address that. They tend to have a little bit lower power than electric double layer capacitors, because you have to wait for these reactions. Even though we call them really fast reactions, you still have to wait a little bit. It's not as fast as just putting a Coulomb force on a charge and it zips away, right? You have to. There is some reaction that happens. There's electron transfer that goes on. Some issues are that these reactions kind of inherit the problems of batteries to some extent. They can be unstable, especially for polymers, and then that produces shorter lifetime, which is problematic. So the cost is particularly an issue for ruthenium, as I mentioned before. The nanostructured carbons are listed here, but they're not really proven. For those of you who study supercapacitors, you might think there have been papers about nanostructured carbons for many years, even decades, in capacitor applications, but there's really not a lot of commercial products out there, so they're not what we would call fully proven yet. The R&D directions are looking at non-carbon electrodes, metal oxides that are nanostructured, right? So instead of taking the carbon and using it as a electrode and a template for your nanostructuring, just nanostructuring the metal oxides themselves. That's an interesting approach, but also looking at different kinds of nanostructured carbons. So ultimately, I think the quest and the reason for studying pseudo-capacitive supercapacitors is that you would want to replace batteries in general for many applications. Maybe not so much because they have more power. You may or may not need their extra power. We know that they're going to beat most batteries on power, but because their cyclability is so much better, right? So you could have essentially something that works like a battery but lasts 100 or 1,000 times longer. Okay, so that's the idea. And you might say, well,